Okay, let's try and solve this in Excel. We're going to have a column of slices here, which will all be at x equals 0 and have y values that go from the bottom to the top of the rod. And then we'll work out the x and y coordinates of the r vector. Then we'll work out the electric field in x and the electric field in y. And then when we're done, we'll add them all up. Now, let's define the length of our rod. Let's make it 1 meter long. And we'll define the position we're going to measure things at. So let's say we're measuring it 5 centimeters off the rod. And we're going to measure it, let's say at y equals 0, which is the midpoint of the rod. Okay. We need to give the rod some charge. Let's give it a nanocoulomb. Right, so we're going to start at the bottom of the rod. So it's going to start at minus L over 2. It's minus L over 2. And then our step, we need a step size. So let's have dy of, let's go up in steps of 1 centimeter. So the new y value here is going to be the old value plus the step size. And then we can drag that down till we get to the top. That's not right. What have I done wrong here? Oh, okay, so there should be dollar signs in front here, because it's getting the step size from the same cell every time. So now if I drag down, it should work. 0.49, let's go up to the top at 0.5, there we go. So it's gone all the way from the bottom to the top of the rod. Now, these x and y are the displacement vector. That's the vector from the slice of the rod that we're considering to the measurement points. So that's just going to be equal to this minus 0. So it's going to be pretty simple. It's going to be that all the way down. Y is going to be the y coordinates measured minus the y of our slice. And this first thing should have dollar signs. So now we should be able to drag these down. That looks reasonable. When we're taking the slice at the top, it's got minus a half, and it's got 0.05 all the way through. So that's given us all the vectors. Now we can use those vectors and the equations we saw earlier. Here's a step equation. We've got 1 over 4 pi epsilon naught, q over L, x squared plus y squared all to the 3/2 power, dy, the step size, times x minus y0 as the vector. Okay, so we're going to need the 1 over 4 pi epsilon naught, which I'll call it the constant. 1 over 4 pi epsilon naught turns out as 9.0 e minus e plus 9, pretty much. Okay, so what's the electric field? So it's going to be equal to 1 over 4 pi epsilon naught dollars times the charge per unit length. Again, we need dollar signs for all of that. Times dy, again with dollar signs. Now this is the x component, it's going to be times that. I'm going to divide it by x squared plus y squared all to the power of 1.5. And we can do the same for y. Let's copy that. Paste it there. Now, what do we need to change? Most things are the same, but instead of the change in x, we've got the change in y. So that's going to be, instead of B5, F dollar, instead of B5 here, we have C5. Okay, so let's drag this down and see what we get. Right, now let's look at the x values. They start as a pretty small x component, as you'd imagine. And it gets bigger and bigger as we get closer and closer. So when you're at values close to 0, it gets quite large. That's about what you'd expect. The strongest electric field components are going to come from the rod nearest the place of measuring things. And then it drops off as you go further down. For y, then it's going to point upwards when you're coming from the lowest parts, which makes sense. Then as you get towards 0, it'll go towards 0 because the electric field is going to point straight outwards. There's going to be no y component. I get a negative value, which becomes smaller and smaller as you go away. So that all makes sense. Now what we want to work out is the sum of these things. So total electric field in x, and that's just going to be equal to the sum of all the x values. Comes out as 358 volts per meter. And now we can do similarly for the total EY. It's equal to the sum of all these. Now that's come out as very, very close to 0. If we change the format here to be number, you can see pretty much is 0. There's going to be a small rounding error, but you'd expect the electric field in Y to be 0 because we're halfway down the rod. However, we could move it to any other position by changing this. So let's say we're half a meter up. Electric field's gone down in x, but increased in y. Whereas if we went to minus 0.5, now it's gone to a negative value. So this all seems to work and look fairly plausible.